there's a planet out there that shouldn't exist. Not according to our theories, not according to our models, not according to anything we thought we understood about how solar systems work. It orbits so far from its parent stars that a single year on this world takes 15,000 Earth years to complete. Imagine that. By the time this planet makes one trip around its suns, human civilization could rise and fall 3 times over. This is HD 106906b, and it's breaking every rule in the planetary formation playbook. 336 light-years away in the constellation Crux, this massive world hangs in space at a distance so extreme that when astronomers first confirmed it, they had to reconsider whether it was even possible. We're talking about a planet 11 times more massive than Jupiter, glowing hot from the heat of its own formation, sitting at a distance from its stars that makes Neptune's orbit look cozy. To put this in perspective, if you could stand on HD 106906b and look back at its parent stars, they would appear as nothing more than bright points of light in a black sky. Twin suns, yes, but so distant they'd barely warm your face. The discovery came in 2013, though the story actually began 8 years earlier. University of Arizona graduate student Vanessa Bailey led the team that finally spotted this cosmic oddball, but the observations that made it possible started back in 2005 at the Magellan telescopes in Chile's Atacama Desert. Astronomers weren't even looking for planets initially. They were studying the debris disk around the star HD 106906, a young system still cluttered with the leftover material from its formation. What they found instead rewrote our understanding of where planets can exist. The numbers alone are staggering. HD 106906b sits roughly 738 astronomical units from its host stars. 1 astronomical unit is the distance from Earth to our Sun, about 93 million miles. Multiply that by 738. The planet orbits at approximately 68 billion miles from home. That's not a typo. 68 billion miles of empty space between this world and the twin stars it circles. But distance is only part of what makes this system so bizarre. The planet's orbit isn't just wide. It's wildly eccentric, stretched into an elongated ellipse that swings it through space on a path tilted 21 degrees away from the flat disk of debris surrounding its stars. Planets aren't supposed to do that. They form inside disks of gas and dust, and they're supposed to stay in roughly the same plane as that disk. It's like the fundamental law of planetary architecture. Yet here's HD 106906b, tilted off-axis, following a trajectory that suggests something violent happened in this system's past. Think about our own solar system for comparison. The 8 major planets all orbit the Sun in roughly the same flat plane, like grooves on a cosmic record player. Sure, there's some variation. Pluto's orbit is tilted about 17 degrees, which is part of why it got demoted from planet status. But HD 106906b makes Pluto's orbital eccentricity look quaint. This is a planet that appears to have been thrown. The host stars themselves add another layer of intrigue. HD 106906 isn't a single star but a binary system, 2 F-type stars locked in a tight orbital dance around their common center of mass. They circle each other in less than 100 days, so close together that most telescopes can't separate them into distinct points of light. These are young stars, just 13 to 15 million years old, still surrounded by the dusty debris left over from their formation. For context, our Sun is 4.6 billion years old. HD 106906s stars are cosmic infants. And they're bright. Combined, these stars pump out approximately 6 times the luminosity of our Sun. They're classified as F5V main sequence stars, yellow-white and hotter than our solar-type star. The system belongs to the Scorpius-Centaurus Association, a collection of young stars all born from the same giant molecular cloud. This association is the nearest OB association to Earth, making it an invaluable laboratory for studying how planetary systems form and evolve. Members of this stellar nursery range from 11 to 15 million years old, all babies on astronomical timescales. Which brings us back to the planet itself. At 13 million years old, HD 106906b is still glowing from the residual heat of its formation. Its surface temperature hovers around 1800 Kelvin, roughly 1500 degrees Celsius or 2700 Fahrenheit. That's hot enough to melt rock. This heat isn't coming from its distant parent stars. No, this is primordial warmth, the planet still radiating away the energy it accumulated when it first coalesced from gas and dust. Because it's so much cooler than its host stars, HD 106906b emits most of its energy in the infrared spectrum rather than visible light. This infrared glow is precisely what allowed astronomers to spot it in the first place. Direct imaging of exoplanets is extraordinarily difficult. Most planets are simply too faint and too close to their host stars to photograph directly. They get lost in the overwhelming glare of starlight, like trying to spot a firefly hovering next to a searchlight. The vast majority of known exoplanets were discovered through indirect methods. The transit technique watches for the tiny dimming of starlight when a planet passes in front of its star. The radial velocity method detects the gravitational wobble a planet induces in its star as it orbits. Both methods work, but neither actually produces an image of the planet itself. HD 106906b is different. Its extreme distance from its host stars, combined with its youth and high temperature, makes it one of the rare exoplanets we can actually see. The planet's infrared signature can be separated from the starlight because there's simply so much empty space between them. It's still incredibly challenging. Even with the separation, capturing an image required cutting-edge technology developed specifically for this kind of work. The breakthrough came through adaptive optics, a technique that corrects for the blurring effects of Earth's atmosphere in real time. Our atmosphere is wonderful for breathing but terrible for astronomy. It causes starlight to blur and twinkle, limiting the resolution ground-based telescopes can achieve. Adaptive optics systems use deformable mirrors equipped with hundreds or thousands of tiny actuators that adjust their shape thousands of times per second. These mirrors compensate for atmospheric turbulence as it happens, delivering images nearly as sharp as those from space telescopes. For HD 106906b's discovery, the team used the Magellan Adaptive Optics System, or MAG-AO, mounted on the 6.5-meter Magellan telescope in Chile. The system's adaptive secondary mirror featured 585 actuators, each moving 1,000 times every second to remove atmospheric distortion. Without this technology, the planet would have remained invisible, just another faint infrared source lost in the noise. But seeing the planet was only the beginning. The real detective work involved confirming that this object was actually gravitationally bound to the star system and not just some random background object that happened to be in the same line of sight. Space is vast. Coincidences happen. The team needed proof that HD 106906b was truly part of the HD 106906 system. They found that proof in the Hubble Space Telescope archives. By comparing images taken 8 years apart, astronomers could measure the planet's motion across the sky. If it were a background object, it would have moved independently. Instead, HD 106906b moved together with its host stars, sharing their common proper motion through space. Statistical analysis showed the odds of this being a coincidence were less than 0.01%. The planet was real, and it was bound. Then came the spectroscopic confirmation. Using the Fire spectrograph, also mounted on the Magellan telescope, the team analyzed the light coming from HD 106906b itself. The spectrum revealed a spectral type of L2.5, later refined to L1.5 with observations from the Very Large Telescope Symphony instrument. This spectral classification confirmed the planet's temperature and provided crucial information about its atmospheric composition. The carbon-to-oxygen ratio in HD 106906b's atmosphere matched that of the stellar association where its host stars were born, a detail that would later prove important for understanding how this strange world came to be. What astronomers discovered in that atmospheric data was troubling. The composition suggested HD 106906b might have formed more like a star than a traditional planet. Its chemical fingerprint was consistent with stellar-like formation, raising uncomfortable questions about whether we should even call it a planet at all. But with 11 times Jupiter's mass, it clearly wasn't massive enough to ignite nuclear fusion and become a star. It occupied an awkward middle ground, neither fully planet nor failed star. The implications were staggering. If HD 106906b formed like a planet, our models couldn't explain how. If it formed like a star, the mass ratio with its host binary was completely wrong. Something unprecedented had happened in this system, and astronomers were only beginning to piece together the story. The problem was that astronomers were staring at an object that shouldn't exist according to every formation model they had. Think about it this way. When you build a sandcastle, you need wet sand. The farther you get from the water's edge, the drier the sand becomes, and eventually you're too far away to build anything at all. Planets form in disks of gas and dust around young stars. But those disks have edges, and HD 106906b was sitting way beyond where any disk should have enough material to build something 11 times Jupiter's mass. The standard model of planet formation is called core accretion. Small particles of dust stick together through static electricity and gentle collisions. Over time, these clumps grow larger, eventually becoming rocky cores several times Earth's mass. Once a core reaches about 10 Earth masses, its gravity becomes strong enough to pull in massive amounts of gas from the surrounding disk, rapidly inflating into a gas giant. This process works beautifully for explaining Jupiter, Saturn, and most of the exoplanets we've discovered. But it has a fatal flaw when applied to HD 106906b. It's too slow. At 738 astronomical units from its host stars, the disk would have been incredibly thin and cold. Particles would have been moving slowly, collisions would have been rare, and building even a small rocky core would have taken hundreds of millions of years. The problem is that protoplanetary disks don't last that long. They dissipate in just a few million years as the young star's radiation blows away the gas or as material gradually falls onto the star. HD 106906b would have needed more time than the disk had to offer. So astronomers considered the alternative. Gravitational instability. This mechanism bypasses the slow buildup entirely. If a region of the disk becomes dense enough and cold enough, it can collapse directly under its own gravity, forming a gas giant in just a few thousand years. No rocky core required. The disk just fragments, and suddenly you have a massive planet. This process can work at large distances where core accretion fails. But gravitational instability has its own requirements. You need a lot of mass in the outer disk, and you need it to be extremely cold so thermal pressure doesn't prevent collapse. Here's where the numbers refuse to cooperate. Observations of the debris disk surrounding HD 106906 showed it simply didn't contain enough mass in the outer regions to trigger gravitational instability. The disk was there, stretched asymmetrically from about 120 to 550 astronomical units from the binary stars, but it was sparse. not nearly dense enough to spontaneously collapse into an 11 Jupiter mass object. Even if conditions had been perfect, which they weren't, the disk's mass budget came up short. Vanessa Bailey, who led the discovery team, put it bluntly, "No model of either planet or star formation fully explains what we see." That statement wasn't scientific caution. It was an admission that astronomers were confronting something genuinely new. Every formation pathway had a deal-breaker. Core accretion was too slow. Gravitational instability lacked sufficient mass. And yet HD 106906b was right there, glowing in the infrared, undeniably real. So the team explored a third possibility, one that blurred the line between planets and stars. What if HD 106906b didn't form as a planet at all? What if it formed as a companion in a binary system, two objects collapsing independently from separate clumps within the same molecular cloud? Binary star systems form this way all the time. Two dense regions in a cloud undergo gravitational collapse simultaneously, and if they're close enough, they remain gravitationally bound, orbiting each other for billions of years. Could HD 106906b be a failed star, a clump that started to collapse but ran out of material before it could ignite nuclear fusion? The idea had appeal. It would explain the extreme separation without requiring an enormous protoplanetary disk. It would account for the rapid formation, since gravitational collapse of a gas clump can happen quickly. And it would justify the planet's unusual chemical composition, which matched the stellar association rather than showing the enrichment patterns typical of planets that form in disks. But there was a massive problem with this scenario too. Mass ratio. When binary stars form, they tend to have relatively similar masses. The most extreme mass ratios observed in binary systems are about 10 to 1. HD 106906 presents a mass ratio of more than 140 to 1. The host binary stars have a combined mass of 2.71 times the Sun's mass. HD 106906b weighs in at 11 Jupiter masses, which translates to roughly 0.01 solar masses. That ratio is wildly outside the range that binary formation theory predicts. Binary formation just doesn't produce companions that are 100 times less massive than the primary. Vanessa Bailey acknowledged this directly. In our case, the mass ratio is more than 100 to 1. This extreme mass ratio is not predicted from binary star formation theories, just like planet formation theory predicts that we cannot form planets so far from the host star. The system was breaking rules in every direction. Too far for planets, too lopsided for binaries. HD 106906b seemed to occupy a forbidden zone of parameter space, a region where nothing should exist according to our theoretical frameworks. But maybe the answer wasn't in how HD 106906b formed, but in where it formed. What if this planet didn't originate at 738 astronomical units? What if it started somewhere much closer to its stars and then got kicked out to its current extreme orbit through violent gravitational interactions? This is where the story takes a darker turn. Because if HD 106906b was ejected, something catastrophic must have happened in the early days of this system. Something powerful enough to fling an 11 Jupiter mass object across interstellar distances without losing it entirely. The leading scenario goes like this. HD 106906b formed relatively close to its host stars, perhaps just a few astronomical units away, inside the main circumstellar disk. At that distance, core accretion could work. Material was abundant, temperatures were right, and a massive planet could grow within the disk's lifetime. Everything was normal, at least initially. But then the planet's orbit began to decay. Gas drag from the surrounding disk pulled HD 106906b inward, forcing it to spiral toward the binary stars. This process, called orbital migration, is common in young planetary systems. We see it everywhere. Hot Jupiters, massive planets orbiting scorchingly close to their stars, almost certainly migrated inward from more distant birthplaces. Migration isn't gentle. As HD 106906b fell inward, it would have disrupted the disk, clearing gaps, stirring up material, and heading toward an eventual close encounter with the central binary. And that's when the binary stars struck back. When HD 106906b got too close, the gravitational effects from the two stars interacting with the massive planet created chaos. Instead of being captured into a stable orbit or crashing into the stars, HD 106906b was flung outward on a highly eccentric trajectory. The binary acted like a gravitational slingshot, hurling the planet toward interstellar space. This kind of scattering event can impart enormous velocities. In most cases, the planet would have been ejected completely, becoming a rogue world drifting through the galaxy with no star to call home. But something stopped HD 106906b from leaving. And that something might have been a passing star. About 2 to 3 million years ago, astronomers discovered using data from the Gaia spacecraft, two stars passed within 1 parsec of the HD 106906 system. That's roughly 3.3 light-years, close enough for their gravity to have a measurable effect. These stellar flybys are more common than you might think, especially in young star-forming regions where stellar densities are high. When a star passes nearby, its gravitational influence can alter the orbits of objects in the system, sometimes stabilizing them, sometimes disrupting them further. In the case of HD 106906b, the passing stars may have provided the crucial intervention that saved it. As the planet was flying outward on its ejection trajectory, the external gravitational tug from the flyby could have altered its path just enough to keep it bound to the system. Instead of escaping into interstellar space, HD 106906b settled into a wide, eccentric orbit, still gravitationally attached to its host stars but now occupying the distant frozen frontier where we see it today. The orbit is bizarre, tilted 21 degrees relative to the debris disk, highly elongated, and taking 15,000 years to complete one revolution. This scenario, violent as it sounds, actually fits the evidence better than any static formation model. It explains the extreme distance without requiring impossible disk conditions. It accounts for the planet's misalignment with the debris disk, a natural consequence of being scattered rather than forming in place. And it provides a mechanism for the disk's asymmetry. The gravitational chaos of the ejection event would have stirred and distorted the surrounding material, leaving the lopsided debris distribution we observe today. But this story raises an uncomfortable question. If this happened to HD 106906b, could it happen elsewhere? Could it happen here? In our solar system? The parallels are unsettling. Our solar system has its own mysteries lurking in the outer darkness beyond Neptune. Objects in the Kuiper Belt, that vast region of icy bodies stretching far beyond Pluto, don't behave the way they should. Their orbits cluster in ways that shouldn't happen by chance. They're aligned, tilted, grouped together as if something massive is pulling strings from the shadows. In 2016, astronomers Konstantin Batygin and Mike Brown from Caltech proposed a radical explanation. They called it Planet 9. A hypothetical world, perhaps 5 to 10 times Earth's mass, orbiting somewhere between 500 and 1,000 astronomical units from the Sun. We've never seen it. No telescope has captured its light. But the math insists it's there. The orbital clustering of distant Kuiper belt objects is too precise to be random. Computer simulations show that without a massive perturber, these orbits should be scattered randomly across the sky. Instead, they point in similar directions, tilted at similar angles, as if shepherded by an invisible giant. The probability of this happening by chance is less than 1 in 10,000. Planet 9, if it exists, would take 10 to 20,000 years to complete one orbit. Sound familiar? HD 106906b takes 15,000 years. Both are massive worlds on extremely elongated paths, far removed from their system's center of gravity. Both are misaligned with the main orbital plane. The resemblance isn't just superficial. Badigian's team has identified 5 independent lines of evidence pointing toward Planet 9's existence. The orbital clustering is just the first. The second is the unusual tilt of the solar system's orbital plane. Something massive has torqued the entire disk of planets by 6 degrees. The third is the presence of highly inclined Kuiper belt objects whose orbits are nearly perpendicular to the main plane. These shouldn't exist without external gravitational influence. The fourth line involves objects on orbits that directly oppose Planet 9's hypothesized path, as if they've been captured into orbital resonance. The fifth is the existence of extremely distant objects with orbits that take them more than 1,000 astronomical units from the Sun, far beyond where natural formation processes should operate. Each piece of evidence independently suggests something massive lurks out there. Together, they paint a compelling picture. But here's where HD 106906b becomes critical. Before its discovery, skeptics could argue that such extreme planetary orbits were purely theoretical, mathematical curiosities with no basis in physical reality. HD 106906b changed that. It proved that massive planets can exist on wildly eccentric, enormously distant orbits. It demonstrated that scattering events can preserve planets in systems rather than ejecting them completely. The formation scenario proposed for HD 106906b mirrors what might have happened to Planet 9. In the early solar system, several planetary cores formed beyond Neptune. Most models suggest there were 5 giant planet cores, not 4. Jupiter, Saturn, Uranus, Neptune, and a fifth world. Computer simulations of solar system formation consistently produce this extra core. It forms naturally in the outer disk where icy material is abundant. But 5 giant planets make for an unstable configuration. Gravitational interactions between them would have been intense during the solar system's youth. Orbits would cross. Close encounters would occur. In most simulations, one planet gets ejected entirely, becoming a rogue world drifting through interstellar space. But in some runs, the ejected planet doesn't quite escape. It gets kicked to the outer edge of the Sun's gravitational influence and stays there, barely bound, on a distant elliptical orbit. That's Planet 9. Potentially. The mechanism is identical to what happened at HD 106906. Formation in the inner regions, migration due to disk interactions, violent scattering by the dominant gravitational players, Jupiter and Saturn in our case, the binary stars in HD 106906's case, and stabilization at extreme distance through external perturbations. For HD 106906b, passing stars provided the stabilization. For Planet 9, it might have been the galactic tide or encounters with other stars in the Sun's birth cluster. The Sun didn't form in isolation. It was born in a dense stellar nursery containing hundreds or thousands of stars, all packed into a relatively small volume. These stars would have passed near each other frequently during the first few million years. One such flyby could have nudged Planet 9's orbit just enough to keep it bound while preventing it from returning to the inner solar system. HD 106906b's existence validates this entire scenario. It shows that the physics works. Planets can survive this kind of violent history. They can be scattered to enormous distances and still remain part of their parent system. The fact that we found one example means the process isn't impossibly rare. But there's a darker implication. If HD 106906b represents a common outcome of planetary system evolution, then many systems might harbor distant, unseen giants. These worlds would be almost impossible to detect around other stars. HD 106906b was only found because it's incredibly young and still glowing with formation heat. An older, colder version would be invisible. Think about that. Thousands of nearby stars might have their own versions of HD 106906b or Planet 9, massive worlds lurking in the outer darkness, undetectable with current technology. We'd never know they were there unless we could track the subtle gravitational influences they exert on their home systems, the same method being used to hunt for Planet 9 in our own backyard. The search for Planet 9 has intensified dramatically. Multiple telescopes are scanning the sky, looking for a faint moving dot against the background stars. It would appear as nothing more than a dim point of light, perhaps magnitude 22 or fainter, requiring the most sensitive instruments to detect. The challenge is enormous. The sky is vast, and Planet 9 could be anywhere along a huge swath of possible positions. Recent surveys have ruled out portions of the predicted orbit, narrowing the search area. But vast regions remain unexplored. If Planet 9 is near aphelion, its farthest point from the Sun, it would be moving incredibly slowly, making it even harder to distinguish from background stars or distant galaxies. Detection might require comparing images taken years apart to spot the subtle shift in position. HD 106906b offers a roadmap. It tells us what to expect. A world that massive, that distant, would have specific observable effects. It would perturb the orbits of anything passing nearby. It would create a gravitational signature in the distribution of smaller bodies. It would subtly influence the orbital dynamics of the entire outer solar system. Researchers are now using HD 106906b as a template, refining their models of Planet 9 based on the observed properties of its exoplanetary cousin. The mass estimates have been adjusted. The orbital parameters have been constrained. The search strategies have been optimized. Every detail learned about HD 106906b feeds directly into the hunt happening right here. What makes this even more fascinating is the possibility that both systems underwent similar evolutionary paths but ended up with different outcomes. HD 106906b survived its ejection and remains visible, at least for now. Planet 9, if it exists, survived as well but has faded into invisibility. Both are relics of violent pasts, frozen records of gravitational chaos that reshaped their home systems billions of years ago. The debris disk around HD 106906 tells part of that story. Its asymmetry isn't random. Computer models show that a massive planet on an eccentric orbit would stir the disk material, creating exactly the lopsided distribution we observe. The cleared inner region suggests that HD 106906b might have swept through closer orbits during its inward migration, scattering or accreting everything in its path before being flung outward. Our solar system's architecture might hide similar clues. The Kuiper belt structure, the distribution of orbital inclinations, the strange gaps in clustering patterns, these could all be fossil evidence of Planet 9's formation and ejection. We're reading the same story in two different languages, separated by 300 light-years but connected by universal physical laws. And here's what keeps astronomers up at night. If this happened at HD 106906, if it potentially happened here, how common is it? How many planetary systems have hidden giants? How many worlds were scattered to the edge of their gravitational prisons and remain there, invisible, waiting to be discovered? The answer might reshape our understanding of planetary system architecture. We've spent decades studying planets close to their stars because those are the ones we can detect most easily. But the outer regions, the frozen frontiers beyond a few hundred astronomical units, remain largely unexplored. HD 106906b suggests those regions might be far more populated than we thought. Every planetary system could have its own distant wanderer, a gravitational ghost haunting the outer darkness. The technology that allowed us to find HD 106906b in the first place tells its own remarkable story. Direct imaging of exoplanets represents one of the most difficult achievements in observational astronomy. You're trying to photograph something a billion times fainter than its parent star. A firefly next to a searchlight. A candle beside the sun. Most exoplanets we discovered weren't actually seen. They were inferred. The transit method detects the tiny dimming when a planet crosses in front of its star. The radial velocity technique measures the gravitational wobble a planet induces in its host. Both methods work brilliantly, but they tell us about planets indirectly, through their effects rather than their presence. HD 106906b changed that equation. Its extreme distance from its host stars, combined with its youth and scorching temperature, made it visible. Barely. The planet glows in infrared wavelengths, radiating away the leftover heat from its violent formation. At 2700 degrees Fahrenheit, it emits enough energy to be detected if you know exactly where to look and have the right equipment. The breakthrough came from adaptive optics. Earth's atmosphere is constantly in motion, turbulent cells of air at different temperatures that distort incoming light. Stars twinkle because of this turbulence. For astronomers trying to capture razor-sharp images, it's a nightmare. Every photon that travels across interstellar space arrives perfectly, then gets scrambled in the last 100 miles. Adaptive optics systems fight back in real time. A deformable mirror with hundreds of tiny actuators adjusts its shape thousands of times per second, compensating for atmospheric distortion. The Magellan adaptive optics system used for HD 106906b's discovery employed 585 actuators, each moving 1,000 times every second. The mirror essentially undoes what the atmosphere does, delivering images nearly as sharp as those from space telescopes. Without this technology, HD 106906b would have remained invisible, lost in the glare of its parent stars. The planet's infrared signature would have been overwhelmed, indistinguishable from background noise. But with adaptive optics removing atmospheric blur and infrared cameras tuned to the right wavelengths, the planet emerged. A faint point of light where theory said nothing should exist. The discovery process started 8 years before anyone knew the planet was there. Observations of HD 106906 began in 2005 at the Las Campanas Observatory in Chile. Astronomers were interested in the debris disk surrounding the young binary star system. They weren't hunting for planets. They were studying dust. Then in 2013, graduate student Vanessa Bailey and her team pointed new instruments at the system. The Clio 2 thermal infrared camera, mounted on the 6.5-meter Magellan telescope, captured something unexpected. A bright infrared source, far from the central stars, moving with them through space. The initial detection had to be confirmed. Was this really a planet bound to HD 106906, or just a background object that happened to appear nearby? The team turned to archival Hubble Space Telescope data from 2004. If the object was gravitationally bound to the system, it would share the star's motion through the galaxy. If it was a background star or galaxy, it would move independently. The Hubble images provided the answer. The object moved with HD 106906. Same proper motion, same distance, same direction. Statistical analysis showed the odds of this being a coincidence were less than 0.01%. HD 106906b was real, and it was bound to its host system. Spectroscopic analysis came next. The Fire spectrograph at Magellan captured the planet's light and split it into constituent wavelengths. This revealed temperature, atmospheric composition, and mass estimates. HD 106906b showed a spectral type of L1.5, indicating a surface temperature around 1820 Kelvin. Its mass came in at roughly 11 Jupiter masses, firmly in the planetary regime but pushing toward brown dwarf territory. What really caught attention was the carbon-to-oxygen ratio in the planet's atmosphere. The measurement matched the stellar association where HD 106906 formed. This suggested the planet might have formed more like a star than a traditional planet, collapsing from its own clump of gas rather than building up through core accretion in a disk. The measurements created as many questions as answers. How does something 11 times Jupiter's mass end up 738 astronomical units from its host stars? The prevailing planet formation models simply didn't allow for it. Core accretion, where planets build up from smaller pieces over millions of years, works too slowly at such distances. The disk material is too sparse, the timescales too long. Gravitational instability, where clumps in the disk collapse directly into giant planets, requires more mass in the outer regions than observations typically show. Neither pathway seemed viable. Yet HD 106906b existed, glowing in infrared images, defying theoretical expectations. The binary star hypothesis emerged as one possibility. Maybe HD 106906b formed independently, like a very low-mass star, from its own collapsing gas cloud. Two adjacent clumps of gas collapse separately, and if they're close enough, gravity binds them together. This happens frequently with binary stars. But the mass ratio created problems. Binary stars typically don't exceed ratios of about 10 to 1. HD 106906's mass ratio exceeds 140 to 1. The primary stars weigh in at 2.71 solar masses combined. The planet barely reaches 0.011 solar masses. That extreme imbalance doesn't fit binary formation scenarios. Vanessa Bailey explained it during the Discovery announcement. Perhaps the planet's progenitor clump was starved for material. It started collapsing like a star but never gathered enough mass to ignite fusion. A failed star frozen in adolescence, bound to its more successful siblings. The alternative theory gained more traction over time. HD 106906b formed closer to its stars, perhaps only 3 times Earth's distance from the Sun. Then something went catastrophically wrong. Drag from the gas disk caused orbital decay. The planet spiraled inward, approaching the binary stars. Their combined gravity grabbed hold and flung it outward in a violent ejection. This scattering scenario explained the extreme orbit but created its own puzzle. If HD 106906b was kicked that hard, it should have escaped entirely. The planet should be wandering interstellar space right now, a rogue world with no star to call home. Yet it remained bound, barely, in a 15,000-year elliptical orbit. That's where passing stars entered the picture. Gaia's spacecraft data revealed two stars, HIP 59716 and HIP 59721, that passed within 3.3 light-years of HD 106906 between 2 and 3 million years ago. Not particularly close by interstellar standards, but close enough. Their gravitational influence could have provided the final nudge, stabilizing HD 106906b's orbit just enough to keep it from flying away completely. Think about the precision required. The planet gets kicked by its host stars, sent tumbling toward ejection. Then, at exactly the right moment, a passing stellar system applies just the right gravitational tug to circularize the orbit slightly. Too little influence and HD 106906b escapes. Too much and it crashes back inward. The window for success is narrow, yet somehow it happened. The 14-year baseline of observations from Hubble proved crucial for understanding the orbital motion. Meijing Guin led the analysis, comparing images from 2004 through 2018. Tracking HD 106906b's position with extraordinary precision revealed the planet's trajectory. The measurements confirmed the 15,000-year orbital period and showed the orbit is highly eccentric, bringing the planet no closer than 500 astronomical units at perihelion. This matters because it means HD 106906b has minimal influence on any inner planets that might exist. The system could harbor additional worlds closer to the binary stars, completely unaffected by their distant companion. The gravitational reach of HD 106906b extends far into space, but it doesn't penetrate the inner system. The debris disk tells another part of the story. It's asymmetric, lopsided, with material distributed unevenly around the central stars. Computer models show this is exactly what you'd expect if a massive planet on an eccentric orbit had plowed through the disk region. HD 106906b would have scattered smaller bodies, cleared certain zones, and stirred the remaining material into the asymmetric pattern we observe. The cleared inner region suggests the planet may have swept through closer orbits during its migration phase. Everything in its path would have been scattered or accreted. The current disk structure represents what survived after HD 106906b's rampage through the system. Every detail we learn about this planet feeds back into our understanding of planetary system formation and evolution. HD 106906b isn't just an oddity. It's a laboratory for studying processes that might be common but difficult to observe. How often do planets get scattered to extreme orbits? How many systems have hidden giants we haven't detected yet? What role do passing stars play in shaping final system architectures? The answers reshape how we think about our own solar system's history. If violent scattering events can preserve planets in distant orbits rather than ejecting them completely, then many systems might harbor these gravitational ghosts. Worlds that formed in crowded inner regions but now haunt the frozen outer darkness, barely bound to their parent stars. And somewhere in that darkness, 300 light-years from here, HD 106906b continues its lonely orbit. A world that shouldn't exist, teaching us that the universe cares nothing for our theories. The connection to our own solar system runs deeper than orbital mechanics. HD 106906b might be showing us what Planet 9 went through billions of years ago. Here's what makes the parallel compelling. Both objects exist at extreme distances from their host stars. Both follow highly eccentric orbits tilted away from the main planetary plane. Both appear to have been scattered outward by gravitational interactions with massive bodies closer to their stars. The formation scenarios match too closely to ignore. Planet 9, if it exists, probably started life in the inner solar system. Models suggest it formed somewhere between the orbits of the giant planets, perhaps as a fifth core that never quite became a full gas giant. Then Jupiter and Saturn, gravitational titans that they are, played cosmic billiards. Their combined influence kicked Planet 9 outward, sending it on an elongated path toward the outer darkness. But Jupiter's influence is overwhelming. If the scattering event had been even slightly more energetic, Planet 9 would have escaped entirely. Instead, something stabilized its orbit at the last moment, preserving it in a distant but bound trajectory. Passing stars are the most likely candidates for that final stabilization, just as they were for HD 106906b. The numbers support this. Statistical analysis shows that young star clusters like the Sun once inhabited would have experienced frequent close stellar encounters. In the Sun's first few 100 million years, other stars would have passed within a few thousand astronomical units dozens of times. Any one of those encounters could have provided the gravitational nudge needed to keep Planet 9 from escaping. HD 106906b demonstrates this process in action. We're watching it play out in real time, or as close to real time as astronomy allows. The system is young enough that the evidence remains fresh. The passing stars that stabilized the planet's orbit did so just 2 to 3 million years ago. In astronomical terms, that's yesterday. What does this tell us about planetary system architecture? More than you might expect. Traditional models assumed planets stay roughly where they form. Maybe they migrate inward or outward through disk interactions, but the changes are gradual, controlled. HD 106906b destroys that assumption. Planets can be violently scattered across hundreds of astronomical units in relatively short timescales. This has implications for how we interpret observations of other systems. When we detect a single gas giant orbiting a star, we're seeing a snapshot. We don't know if that planet has siblings that were ejected long ago. We can't tell if the architecture we observe is stable or just a temporary configuration between scattering events. HD 106906b survived because the timing was perfect. The planet got kicked at exactly the right moment for passing stars to stabilize rather than eject it completely. Change any variable slightly and the outcome changes. Kick it harder and it escapes. Softer and it falls back inward. The passing stars arrive earlier or later and their influence misses the critical window. How many planets weren't so lucky? How many Jupiter-mass worlds were scattered into interstellar space during the chaotic early phases of system formation? We have no way to count them, but the physics suggests they should be common. For every HD 106906b that survived, perhaps dozens were lost. This changes how we think about planet formation efficiency. When astronomers model how many planets should form around a given star, they typically assume most of the solid material in the disk gets incorporated into planets that remain bound to the system. HD 106906b suggests that assumption is wrong. A significant fraction of planetary mass might be ejected entirely, wandering the galaxy as rogue planets with no parent star. The atmospheric composition of HD 106906b adds another layer to this story. Spectroscopic analysis reveals a carbon-to-oxygen ratio of approximately 0.53, with significant uncertainty but clearly measured. That ratio matches the composition of the Scorpio-Centaurus stellar association where HD 106906 formed. Why does that matter? Because if HD 106906 be formed like a traditional planet, accreting material from a circumstellar disk, its composition should differ from the parent stars. Planets inherit the composition of their formation location within the disk, which varies with distance from the star. The fact that HD 106906b's composition matches the stellar association suggests it may have formed more like a low-mass star or brown dwarf. This supports the binary formation hypothesis. Two clumps of gas collapsing from the same molecular cloud would naturally share chemical compositions. The challenge remains that the mass ratio is completely wrong for typical binary systems. HD 106906b has about 1/140th the mass of its host binary. Binary stars rarely exceed mass ratios of 10 to 1. So we're left with an object that has the composition of a star but the mass of a planet, orbiting at a distance that makes no sense for either formation pathway. Vanessa Bailey, who led the discovery team, summarized it perfectly when she said no model of planet or star formation fully explains what we see. Maybe the categories are wrong. Maybe we're trying too hard to classify HD 106906b as either planet or failed star when it represents something in between. A hybrid object that formed through a process combining elements of both pathways. Nature doesn't care about our taxonomies. The direct imaging capability that revealed HD 106906b represents a crucial technological achievement. Most exoplanets are discovered indirectly through transits or radial velocity measurements. We infer their presence from effects on their host stars. Direct imaging is different. We're actually seeing the planet itself, detecting photons that originated from its atmosphere. This is extraordinarily difficult. Planets are typically 1 billion times fainter than their host stars in visible light. They're lost in the glare, like trying to spot a firefly next to a searchlight. HD 106906b is visible only because of its extreme youth and separation. At 13 million years old, it still glows from formation heat, emitting strongly in infrared wavelengths. And at 738 astronomical units, it's far enough from its host stars that their light doesn't completely overwhelm it. The Magellan Adaptive Optics system made the discovery possible. Adaptive optics corrects for atmospheric turbulence in real time using deformable mirrors with hundreds of actuators. For HD 106906b, the MAG-AO system deployed 585 actuators adjusting 1,000 times per second. This removed the atmospheric blurring that would otherwise make direct imaging impossible from ground-based telescopes. Without adaptive optics, HD 106906b would have remained invisible. The planet's infrared signature would be smeared across multiple pixels, blended with scattered starlight, effectively undetectable. With adaptive optics, the image sharpens. The planet becomes a distinct point of light, separable from its host stars. The fire spectrograph confirmed the planetary nature of the detection. Spectroscopy reveals what an object is made of by analyzing how it absorbs and emits light at different wavelengths. HD 106906b spectrum shows characteristics consistent with a young, hot planetary atmosphere. The spectral type is L1.5, placing it in the category of brown dwarfs and massive planets with temperatures around 1800 Kelvin. Comparing Hubble images from 2004 with newer observations proved the object shares common proper motion with HD 106906. It's moving through space together with the host stars, not just appearing nearby by chance. Statistical analysis showed the probability of coincidental alignment is less than 0.01%. HD 106906b is definitely part of the system. Every detail we extract from this system feeds into broader questions about how planetary systems form and evolve. HD 106906b isn't just a curiosity. It's evidence that our models are incomplete. The universe contains formation pathways and evolutionary histories we haven't fully mapped yet. Objects that challenge our categories and force us to expand our theoretical frameworks. And if HD 106906b formed through a violent scattering event that nearly ejected it from its system, preserved only by chance encounters with passing stars, then how many other systems have similar hidden giants? How many distant planets orbit in frozen exile, barely bound to stars they rarely approach? The search for Planet 9 takes on new urgency in this context. HD 106906b proves such objects can exist and persist. The orbital dynamics work. The formation scenario is plausible. We're no longer speculating about hypothetical processes. We're observing them directly in another system. That realization shifts everything. The hunt for Planet 9 isn't purely theoretical anymore. We've watched this exact scenario play out elsewhere. A massive planet, ejected to a distant eccentric orbit, stabilized by passing stars, persisting for millions of years. The difference is distance. HD 106906b sits 336 light-years away. Planet 9 might be hiding in our own celestial backyard. The evidence for Planet 9 keeps accumulating. Konstantin Batygin and Mike Brown at Caltech proposed its existence in 2016 based on peculiar clustering patterns among distant Kuiper belt objects. These trans-Neptunian bodies have orbits aligned in ways that seem statistically improbable without a massive perturbing influence. 5 separate lines of observational evidence now point towards something massive lurking in the outer solar system. An object with roughly 10 times Earth's mass, orbiting 20 times farther out than Neptune. The formation scenario mirrors HD 106906b almost perfectly. Planet 9 likely formed in the inner solar system alongside the other planets. Jupiter's overwhelming gravitational dominance then kicked it outward. Jupiter is the 800-pound gorilla of our planetary family. When it interacts gravitationally with smaller bodies, those bodies usually lose. Planet 9 would have been flung into a highly eccentric orbit, possibly headed for interstellar space. Then passing stars stabilized it. The same process that rescued HD 106906b from exile. Think about the timing required for that sequence. A planet gets ejected at just the right angle and velocity to avoid complete escape. Then within a relatively short window, measured in millions of years, another star passes close enough to gravitationally nudge the orbit into a stable configuration. Not so close that the interaction disrupts everything, but close enough to provide the necessary orbital correction. The precision involved is staggering. HD 106906b survived this process 13 million years ago. We're seeing the aftermath directly. Planet 9, if it exists, went through the same gauntlet perhaps 4 billion years ago when the solar system was still densely populated with debris and interacting with sibling stars from its birth cluster. We can't image Planet 9 directly because it's too far, too cold, too faint. But we can study its analog 336 light-years distant and extrapolate backward. The search continues with increasing sophistication. Modern surveys scan the sky systematically, looking for moving objects that don't fit known orbital patterns. The Vera Rubin Observatory, once operational, will image the entire visible sky every few nights. If Planet 9 is out there, reflecting enough sunlight or emitting enough infrared radiation, we'll eventually spot it. The key word is eventually. Space is vast. Even our own solar system contains regions we've barely explored. Every negative result refines the search parameters. We can rule out certain orbital configurations, certain brightness ranges, certain regions of sky. The possibility space shrinks with each survey. Either Planet 9 exists within that remaining volume, or the orbital clustering of Kuiper belt objects requires a different explanation. Maybe a primordial black hole. Maybe multiple smaller objects. Maybe gravitational perturbations from the galactic tide we haven't properly accounted for. HD 106906b proves the Planet 9 scenario is physically plausible. That matters enormously. Before direct confirmation of similar systems elsewhere, the Planet 9 hypothesis remains speculative. You could argue the math worked, but nature might not actually produce such configurations. Now we know nature does exactly this. The pathways exist. The mechanisms function. Planetary systems undergo violent reorganizations that leave massive worlds stranded in frozen exile. What does HD 106906b's atmosphere look like? At 1500 degrees Celsius, it's hot enough that complex chemistry occurs in the upper layers. Spectroscopic measurements show molecular absorption features consistent with methane, water vapor, possibly carbon monoxide. The carbon-to-oxygen ratio matches the stellar association where it formed, suggesting the planet's composition reflects its birth environment. That detail supports the failed star hypothesis over traditional planetary formation. Future observations with James Webb Space Telescope will probe deeper into that atmosphere. Webb's infrared capabilities are ideally suited for characterizing warm exoplanets. Will map temperature gradients, identify additional chemical species, potentially detect weather patterns. HD 106906b becomes a laboratory specimen. A place where we can test atmospheric models for objects in that awkward mass range between planets and brown dwarfs. The debris disk surrounding HD 106906 adds another layer of complexity. That disk is asymmetric, warped, clearly disturbed by gravitational interactions. HD 106906b's orbit is tilted 21 degrees relative to the disk plane. This misalignment is evidence of violent dynamical history. Planets forming peacefully within a disk remain aligned with it. Misalignment signals disruption. Either the planet formed elsewhere and scattered into its current orbit, or passing stars tilted the entire system's geometry. Detailed modeling of the disk structure reveals gaps and clumps that suggest ongoing gravitational perturbations. HD 106906b's eccentric orbit brings it close enough every 15,000 years to stir the outer regions. That periodic stirring prevents the disk from settling into equilibrium. We're watching active dynamical evolution, frozen mid-process for our inspection. Could there be additional planets in the HD 106906 system? The search continues. If HD 106906b scattered outward after forming closer in, what scattered it? The Discovery team found no massive companions beyond 35 astronomical units. But smaller planets could easily hide in the inner system, masked by stellar glare. Multi-planet systems often exhibit complex interactions. One planet's exile might indicate others remain closer, shepherding the debris disk, maintaining the system's peculiar architecture. The Scorpio-Centaurus association provides context for HD 106900SXS youth. This stellar nursery, the nearest OB association to Earth, contains hundreds of young systems all born from the same molecular cloud. Ages range from 11 to 15 million years. HD 106906 fits right in that demographic. By studying multiple systems within the association, we can compare evolutionary states. Some will have debris disks. Others won't. Some will show evidence of giant planets. Others remain undetected so far. Statistical studies across the association reveal how common different planetary architectures are. Do most young systems undergo violent reorganizations like HD 106906? Or is this system an outlier, a rare catastrophic configuration? The answer shapes our understanding of planetary system formation as a whole. If dramatic scattering events are common, then stable configurations like our own solar system might be the exception rather than the rule. That possibility is humbling. We've spent centuries assuming solar system architecture is typical. 8 planets in roughly circular orbits, organized by size and composition, all aligned in the same plane. Orderly. Predictable. Stable for billions of years. HD 106906 suggests that's one possible outcome among many. Other systems take wildly different paths. Ejected giants. Misaligned orbits. Ongoing chaos. The formation timescale matters too. HD 106906b exists at 13 million years old. Its violent history already happened. The scattering, the near ejection, the stabilization by passing stars, all completed within the first few million years after formation. Planetary systems aren't static arrangements that form and persist unchanged. They're dynamic environments where gravitational interactions reshape everything multiple times before settling into long-term stability. Our solar system went through similar upheaval. The NICE model proposes that Jupiter, Saturn, Uranus, and Neptune formed closer together and migrated outward through gravitational interactions with a primordial debris disk. That migration triggered the late heavy bombardment, scarring the inner planets 4 billion years ago. We see evidence in lunar craters, Martian geology, Earth's oldest rocks. Planet 9 might be a remnant from that chaotic period. A fifth giant that didn't quite escape but didn't settle into a normal orbit either. HD 106906b shows us what that remnant looks like from outside. A massive world glowing faintly in the darkness, completing one orbit every 15,000 years, barely connected to the system that birthed it. If Planet 9 exists, it's experiencing the same isolated existence. No seasons. No changing stellar phases. Just endless slow revolution through the void. What happens to HD 106906b over the next billion years? Its orbit is stable now, but systems evolve. The host stars will eventually exhaust their hydrogen fuel and expand into red giants. The debris disk will dissipate as material gradually spirals inward or gets ejected. HD 106906b itself will cool, fading from infrared visibility as its formation heat radiates away. In a few hundred million years, it'll be nearly impossible to detect. A cold dark sphere on an enormous orbit, invisible except through gravitational effects. That future state resembles what Planet 9 is now. Too cold to glow. Too distant to reflect much sunlight. Detectable only through its influence on other objects. HD 106906b gives us a glimpse of the endpoint while still being observable in its hot youth. The parallels between these systems extend beyond simple orbital mechanics. Both formed in dense stellar environments where gravitational interactions were common. Both underwent violent ejection events. Both were stabilized by external influences rather than internal system dynamics. Both challenge our categories and force theoretical expansion. HD 106906b isn't an answer. It's a mirror. When we look at this system, we're seeing possibilities for our own. Pathways that might have been taken. Configurations that could exist just beyond our current detection limits. The universe is showing us that planetary systems are stranger, more diverse, more dynamic than we imagined. And somewhere in our outer solar system, in the frozen darkness beyond Neptune's orbit, Planet 9 might be waiting to prove the point. Looking up at the night sky, most of us think of planets as orderly companions to their stars. Mercury through Neptune, arranged like clockwork, predictable, stable, following rules we learned in school. HD 106906b destroys that comfortable picture completely. This 11 Jupiter-mass giant wandering through space 738 astronomical units from its host stars represents something profound. Not just an anomaly in our catalogs, but evidence that planetary systems routinely undergo catastrophes we're only beginning to understand. The violence required to fling a massive world to such extreme distances, the precision needed for passing stars to stabilize rather than eject it completely, the sheer improbability of the entire sequence, it all happened. We photographed the result. Every detail we extract makes the implications clearer. The spectroscopic data showing stellar-like composition. The 14-year baseline of orbital tracking confirming a 15,000-year period. The asymmetric debris disk bearing scars from gravitational chaos. The carbon-to-oxygen ratio matching the stellar association. The misalignment with the disk plane. Each measurement adds weight to a scenario that sounds like science fiction but represents observed reality. Planet 9 becomes more than speculation in this context. We're not extrapolating from mathematical models anymore. We're comparing to a real system where the exact same dynamics played out and left a survivor. The formation pathway exists. The scattering mechanism works. The stabilization through stellar flybys happens. Nature does this. The question shifts from whether such objects can exist to how many are out there hiding in the darkness. The search continues with new urgency. HD 106906b proved that massive planets can persist on wildly eccentric orbits far beyond what formation theory predicted. If it happened there, if it potentially happened here, how common is this outcome? How many nearby stars harbor their own distant giants invisible to current surveys? We might be surrounded by these gravitational ghosts and not know it. The technology that revealed HD 106906b, adaptive optics correcting atmospheric turbulence in real time, infrared cameras capturing formation heat from young worlds, represents just the beginning. James Webb Space Telescope will probe deeper into these systems. Next-generation ground-based telescopes with larger mirrors and more sophisticated adaptive optics will push the detection limits further. We'll find more examples. We'll refine the statistics. We'll understand whether HD 106906b is exceptional or routine. But right now, this moment, we're staring at something that challenges fundamental assumptions about how planets form and where they end up. An object that defies easy classification. Too massive to be a traditional planet. Too light to be a star. Orbiting too far to have formed there. Tilted too steeply to have grown peacefully in a disk. Every property pushes against theoretical boundaries. The universe doesn't care about our categories. It produces what physics allows, and we're forced to expand our frameworks to accommodate reality. HD 106906b exists because the conditions permitted it. The initial formation, whether through core accretion or gravitational instability or some hybrid process we haven't fully characterized. The inward migration driven by disk drag. The violent ejection by the binary stars. The chance encounter with passing stars that prevented complete loss. Each step had to occur in sequence, and the odds of success were minuscule. Yet here it is. That's what makes astronomy humbling. We construct elegant theories based on our local experience, then discover the universe has been running experiments we never conceived. HD 106906b is one data point among billions of planetary systems in our galaxy alone. One configuration among infinite possibilities. And it's teaching us that the stable, orderly arrangement of our solar system might be unusual. A fortunate outcome in a cosmos where chaos is common. 336 light-years away, a lonely world continues its slow orbit through the void. Too far from its suns to feel their warmth. Too massive to be called a simple planet. Too young to have cooled into invisibility. A transitional object caught between definitions, between formation and final state, between the inner system and interstellar space. HD 106906b occupies a boundary zone, and boundaries are where we learn the most. The planet won't stay visible forever. In a few 100 million years, as formation heat dissipates and the glow fades, it'll become undetectable except through gravitational influence. Future astronomers studying the HD 106906 system might only infer its presence from perturbations in the debris disk, from subtle wobbles in the host star's motion, from gaps in orbital distributions. They'll hunt for it the same way we're hunting for Planet 9 now. And maybe that's the deepest lesson here. The things we can't see directly often matter most. The processes that shaped our own solar system 4 billion years ago left only faint traces. We reconstruct that history from crater distributions, from isotope ratios in meteorites, from computer simulations informed by observations of younger systems like HD 106906. We're detectives working with incomplete evidence, building narratives from fragments. HD 106906b gives us a fresh fragment. A crucial piece of the larger puzzle about how planetary systems evolve from birth through maturity. It won't be the last such discovery. As our instruments improve and our surveys expand, we'll find more examples of extreme architectures. More planets on unlikely orbits. More systems that defy simple explanation. Each one refines our understanding incrementally. But this particular world, this massive wanderer barely clinging to its parent stars, will remain significant. It was among the first directly imaged exoplanets. The first to demonstrate that scattering events can preserve rather than eject. The first clear analog to the hypothetical Planet 9. The first system where we could track orbital motion over a 15,000-year period using just 14 years of observations. Somewhere in the frozen outer reaches of our solar system, another massive world might be completing its own lonely circuit. Different mass, different distance, different history, but fundamentally similar. A planet that formed in warmth and light, only to be cast into permanent exile through gravitational violence. HD 106906b tells us that world could exist. The physics permits it. The formation pathways support it. The stabilization mechanisms preserve it. Now we just have to find it. The search continues, informed by everything we've learned from studying HD 106906b. Refined orbital predictions. Better understanding of formation scenarios. Improved detection strategies. Enhanced telescopes scanning deeper into the infrared. Statistical models incorporating scattering dynamics. Every advance brings us closer to answering whether Planet 9 is real or whether the clustering of Kuiper belt orbits requires a different explanation. Either outcome matters. Confirmation would validate the HD 106906 analog and prove our solar system underwent the same violent reorganization. Non-detection after exhaustive searches would force us to reconsider the evidence and explore alternative explanations. Both paths advance knowledge. HD 106906b won't provide the final answer. It's not supposed to. It's evidence that certain processes occur in nature. A reference point for comparison. A reminder that the universe contains configurations we haven't imagined yet. 336 light-years might as well be infinite given current technology, but the lessons cross that distance at the speed of light. The photons that left HD 106906b's glowing atmosphere in the year 1688 are reaching Earth now, carrying information about a world that challenges everything we thought we understood about planetary formation. Those photons, captured by adaptive optic systems and sorted by spectrographs, tell a story of exile and survival. Of a planet that shouldn't exist but does. Of orbital mechanics pushed to extremes. Of gravitational chaos giving way to tenuous stability. Of worlds wandering far from their stars, barely bound, slowly circling through darkness that will last billions of years. And in that story, we see reflections of possibilities closer to home. A ninth planet hiding beyond Neptune. A massive world on an orbit so elongated it spends millennia in the outer darkness before briefly sweeping through closer regions. A gravitational shepherd influencing everything around it while remaining invisible. HD 106906b proves such objects exist. Whether one exists here remains the great unanswered question of our time. The answer is out there, encoded in orbital perturbations we haven't measured yet, in infrared signatures we haven't detected, in gravitational influences we're only beginning to map. HD 106906b showed us what to look for. Now we look.